Hello everyone, this is Ling-Jyh from Academia Sinica, Taiwan. Today I would like to share our research project called AirBox, which is a participatory sensing project for PM2.5 monitoring. And I would like to talk about how we can make sense of IoT systems using AirBox as an example. The motivation of the work came from the observation that the air quality of our environment has been getting worse in the last decade. Based on the WHO report published in 2014, about 7 million people were dead in 2012 due to either indoor or outdoor pollution. Among all kinds of air pollutants, PM2.5 is the most important pollutant that can impact our health. By definition, PM2.5 stands for tiny particulate matters with a diameter less than 2.5 micrometers. Since it is very small, it can enter our lung system through the nose and throat. It can penetrate deep into the lungs and travel all the way in our body, causing lung and heart problems, and delivering harmful chemicals to the blood system. Traditionally, we rely on professional monitoring stations by government EPA to understand the air quality. These stations are generally very huge and expensive, and they are deployed to major well-mixed atmosphere. That means they are deployed about 10 meters above the ground with good air circulation and away from emission source. However, since these stations are very expensive, they cannot be deployed everywhere at high density. So, our research question is, can we deploy a small and low-cost air quality sensing device such that everyone can have one and use it to know the air quality of their surroundings? Moreover, if we can have more and more devices deployed, can we do something together and provide finer-grained air quality data to enable something that could not be done before? Now, let me spend some minutes to quickly go through the development of the project. There are three components of the project. The first one is to enable and make low-cost air quality sensing possible. We started the project from scratch about 7 years ago, and gradually we learned how to assemble sensors together, how to make PCB boards, how to send data out from the sensor using Wi-Fi, Bluetooth, or 4G, and how to design 3D printout enclosure. We also evaluate all kinds of low-cost air sensors against professional devices and figure out good sensors that can be used in our project. Fortunately, we found one PM2.5 sensor that is low cost and of good performance for the project. The second component of the project is to empower people to use this technology and duplicate our work to make their own. We decide to use open hardware that is commercially off the shelf and easy to be used, modified if needed. We also release our source code on GitHub, so people can trace our codes and even contribute to our codes. Finally, we decide to release all collected data in open data format and in real time. The idea behind this is threefold. Number one, we want to reduce the technical boundary so everyone can join our project with ease. Number two, we want to build trust between participants and us because everything is open. Number three, we want to recruit more people with diversity. For instance, people can join our project by making a device to contribute data, fix our codes, or contribute new features, or just use our data for his research or develop new applications. The third component of the project is to engage people to participate, collaborate, and contribute. The project started as an academic research project, and then we start working with local community called Location Aware Sensing System, or LAS, to recruit people of different backgrounds. Then, we are lucky to receive a 4-year government grant called Civil IoT Taiwan to deploy AirBox devices in every K-12 school in Taiwan. The focus of the project also evolved over time. It started with a focus on sensor deployment in the beginning and shift to data analysis after collecting a lot of data from the deployment. Now we focus on cross-disciplinary collaboration to address real-world problems. So, the project has built a very positive and healthy ecosystem involving academia, community, industry, government, and education schools and teachers. The 5 components contribute to the system voluntarily and help each other to keep the ecosystem circulating. So far, the project has reached more than 15,000 deployments in 58 countries. We have established tight collaboration with major research universities in Taiwan, as well as in other major low-cost air sensing projects all over the world. In addition to deployment and setting up the network, we also come up with several research results. For instance, we came up with a comprehensive set of evaluation to compare our devices against professional equipment and to evaluate the consistency performance among AirBox devices. Of course, the results are all very encouraging and promising. To deal with thousands of real-time IoT data streams, we also developed a robust backend architecture that can listen to a large number of devices, store data properly into different databases, and release measurement results about real-time in JSON and CSV format. Using the collected data, we implemented the inverse distance weighting algorithm to interpolate the air quality in between AirBox devices. And we took snapshots of the visualization results every 20 minutes to make animations to visualize how air quality distribution changes over time. For instance, on the right-hand side, the first animation shows the long-range transport of dust and pollutants from the north of Taiwan to the south side. This animation was made in the January of 2014. In fact, this was the first time in the history that we can cross-source low-cost air sensor data and visualize such pollution event with such granularity. On the other hand, the second animation was taken during a cultural event in the central Taiwan. During that event, people burnt incenses and ghost money at almost the same time. As we can see in the animation, the air quality of the central Taiwan turns into purple color, indicating very high PM2.5 concentration, and then it changed back to orange color after the event. It turns out to be a perfect material for environment education because human behavior may impact our environments, especially when a large group of people do things together. We also consider the data quality issue in our system and conduct an anomaly detection framework, ADF, to detect pollution events and anonymous devices using spatial temporal data analysis. This work is in fact very challenging because 1. The accuracy of the device is not as good as EPA stations, so our solution has to tolerate slight errors in the data streams. 2. The devices are not time synchronized, so our solution has to implement time window concept in our data analysis. Number 3. The solution has to distinguish outliers and air quality events even though they have similar patterns in the time series data stream. Number 4. The solution has to be simple and fast, so it can support online computation and release the results for further applications in almost real time. The idea of the ADF approach is to detect 2 types of anomaly from the sensor's data stream. The first type is called spatial anomaly. That means an AirBox device behaves differently to the other devices in his neighborhood. The second type is temporal anomaly. That means an AirBox has dramatic changes in his measurement data in a very short time period. Based on the frequency of such 2 anomaly types, we can calculate a trustworthy value for each AirBox device. And based on the appearance patterns of the 2 anomaly types, we can guess out the reasons of such anomaly. For example, it may be located indoors, or maybe there are fixed emission sources near the device, or maybe there is a burning event ongoing near the device. As you can see on the slide, we have successfully implemented our anomaly detection framework and released our results in almost real time. So our analysis results have been imported by the Zero Government Organization, which is the hacker community in Taiwan, and they have created a pretty looking visualization of our data on their website. In their design, they have provided different icons to indicate AirBox devices of different properties, so people can easily get the idea of the device when looking at the PM2.5 website. We also apply machine learning to the AirBox dataset and conduct PM2.5 data forecast research to predict short-term PM2.5 concentrations. To forecast PM2.5 concentrations for the next 1 to 5 hours. Comparing to traditional data forecast problems, short-term PM2.5 forecast is very challenging because you have to train a model, update it frequently, and give the prediction results in a very tiny manner. For instance, you may have only 1 minute to complete the whole work and yield the prediction results for 10,000 AirBox devices. To tackle this problem, we consider the solutions in 2 dimensions. One is accuracy, which means we would like to have a solution that can give us as accurate results as possible. And to make it, we can apply modern machine learning techniques like the neural network or even deep learning to achieve high accuracy prediction. But the training phase may take too much time to make the solution feasible. The other dimension is scalability, which means we want to produce prediction results for as many AirBox devices as possible. For example, we can model the prediction problem as a matrix optimization to find out the transition matrix between 2 consecutive time slots. Then, we can apply the transition matrix to produce data forecast results for the next time slot very quickly, though the error is larger and accumulated. Apparently, the 2 dimensions are contradictory to each other, and there must be something in the middle. So we investigate different clustering techniques to identify different groups of AirBox. They share similar spatial temporal behaviors, and conduct training models for each group. Then we apply the model to the other AirBox devices in the same group to produce forecast results. As you can see on the performance results, there is a significant drop in the computation time, while the accuracy performance is still acceptable. This is just an attempt to strike a good balance between accuracy and scalability, and more research results on the topic are still ongoing, and we hope to have new results very soon. Next, once we have real-time PM2.5 data from dense deployment and short-term prediction data from the forecast service, we developed a new navigation service called Clean Air Routing to provide the minimal PM2.5 exposure route for people traveling in the city. By saying minimal PM2.5 exposure, we are saying the total accumulated PM2.5 over time in your move. As you can see, if you want to travel from the red dot on the right-hand side to the other red dot on the left-hand side, the Google Map shortest path algorithm will give you the gray color path. However, our car algorithm will give you the blue one, which will go to the riverside and then change to the downtown area where there were few vehicles at that time. The total PM2.5 exposure score is reduced from 75 to 59, though the travel time is about 30 minutes more than the shortest path. The car application is just an attempt to design innovative applications based on the low-cost air sensors IoT systems. By providing finer-grained spatial temporal measurement data, we believe there will be more and more new applications created. These applications are essential for IoT systems, not only because they could not be possible without IoT deployment, but also because they make sense of IoT systems and make IoT perceivable for the general public. Recently, we also work with cross-disciplinary experts to address classic problems in other fields. For instance, in spatial statistics and public health, it is essential to predict ground-level PM2.5 concentrations using nearby air quality data, and the results can benefit health impact assessment of cohorts with PM2.5 exposures. Traditionally, the prediction considers EPA station data, meteorological data, and spatial attributes. One of the state-of-the-art work published in 2018 reported the accuracy results with a R-squared value ranging from 0.66 to 0.87 and RMC between 5 and 12.9 microgram per cubic meters. On top of this work, we work with statistic experts to consider data from the AirBox network. We adjust the interpolation parameters based on AirBox data analysis, and the results are very promising. The R-squared value is more stable at 0.87, and the RMC is reduced to 4.1 microgram per cubic meters. The results of this study may benefit many ongoing public health studies in finding the correlation between PM2.5 exposure and different diseases. And we are still working on improving prediction accuracy of the work and looking for collaborations too. Currently, we are working with Taiwan EPA to build a dynamic calibration framework to calibrate low-cost AirBox data. First of all, we chose 31 EPA stations as the reference site and deployed 2 AirBox devices per station to conduct location comparison testbed. Then, for each of the reference sites, we consider more than 200 models and choose the one with the best performance of the day as the calibration model for the reference site on that day. Then, for each AirBox device in Taiwan, we find the nearest reference site to that device and apply its calibration model to the AirBox. We believe there may be some models that can yield better accuracy results in calibration, but this is the best effort result so far we can achieve given our limited technology and computation resources. Using the calibrated data, we also give activity suggestions when releasing the measurement results to the public. In addition, we also release the models on the website in binary form, as well as the detailed parameter configurations in case people would like to reproduce the results. We believe that it is essential to keep everything open in the calibration process, because this is the best way to build and maintain trust for the general public. It is also important for the research community, as we need to ensure the results can be reproduced in the future. In 2017, we are fortunate to receive a 4-year government grant to deploy our devices in every K-12 school in Taiwan. This is not just a deployment project. We received many technical and non-technical feedbacks during the period, and many of them have been put into design to further improve the device. For instance, we have added the OTA feature to allow online upgrade of device firmware. We have added a security chip in the device to achieve per-device data encryption for IoT security. We have switched communication techniques from campus Wi-Fi to nationwide NB-IoT, and we also improve our installation guidelines to ensure the device is correctly installed. Moreover, we also developed side projects to investigate mobile sensing using drones, vehicles, and even bicycles. And recently, we also integrate gas sensors and noise sensors to collect more environment information into the system. The results of this project have made some impact to the society. Today, Taiwan EPA has employed local sensors in the industry area for law enforcement of illegal emissions. And more importantly, EPA has agreed that low-cost air sensors can play an important role in smart environmental governments in the future. So, the project has made some impacts. The data portal of the project has become the most popular one for low-cost PM2.5 sensing in the world. It provides fine-grained PM2.5 data for exposure monitoring of cohorts in health impact assessment studies. encouraged people to apply low-cost and portable sensors for microenvironment monitoring, resulting in large-scale, real-world, and spatial temporal data sets for innovative researches. And here is the take-home messages. We present a participatory PM2.5 sensing system called AirBox, and the lessons learned from the project is open is the way to make systems scalable. The power of Internet of Things is to make sense of data, and we should always think about must-have rather than nice-to-have. There are lots of open challenges, and we look forward to collaborating with you. Thank you.